Welcome to another video about a topic in chemistry. For this video, I'm going to go over orbital hybridization, at least the way that I teach it to my students. If you have never heard about it before, or maybe you're already reviewing and trying to understand it a little bit more, hopefully I can help. In order to understand orbital hybridization, you have to know what an orbital is. You would be studying this in the atomic structure unit for chemistry, and an orbital, as it says here, is not the path an electron takes. It's not an orbit. It's a region of space around the nucleus of an atom where we're likely to find an electron. This was determined by a whole lot of work by a whole lot of different scientists that came together and realized that the interaction of energy and electrons in an atom was such that the energy, a photon would knock an electron off its course. So they were able to essentially plot these 3D areas or regions where electrons are likely to be found, but not the path that they take. And some major heavy duty mathematics with probability and science to describe the whole idea of the layout of electrons in an atom. I'm assuming in this video that you do have a bit of knowledge on what's known as electron configurations, the order in which electrons fill up an atom and where they're likely to be found. Every atom has its own electron configuration. The electrons within the atom possess their own amount of energy, and this is a basic fundamental in chemistry to know. Let's check it out. I like to use an example as my anchor, something that I can always go back for understanding, and this is my recommendation for you. Let's take the atom carbon. Carbon has 6 electrons. Now, the electron configuration for carbon when it's alone, and the way we write it, and then carbon when it's bonded to other atoms is different. And that's what we're going to go over with this orbital hybridization. But let's check out the carbon atom electron configuration first. Here we have 1s2, 2s2, 2p2. This is part of the quantum mechanical model, the present day model that we use. The big numbers, the 1s, the 2s, 3, 4s, are what's known as the principal energy levels. They are the big levels where we're finding electrons. You're reading this from left to right. So on the left-hand side here would essentially be a nucleus, and we're filling up the electrons from closest to the nucleus to farther away. Now, within the second principal energy level, there are a total of 4 electrons. But what scientists have found, both experimentally and what works with the mathematical model, is that 2 of those electrons are in an orbital that is a 3-dimensional spherical shape. And then 2 electrons are each in what's known as a p sublevel, which are almost like lobes. We call it the dumbbell shape, but likely to be found in an upper or lower region by the with the nucleus in the middle, or left and right, or into the paper and out of the paper, since unfortunately we're dealing with 2 dimensions here in a 3-dimensional model. I have a really good video I always show my students with decent graphics, which an attempt at 3D modeling, which I'll put in the description, that you might want to check out for further understanding of the shapes of these sublevels and the orbitals right within those sublevels. But this is the electron configuration. A basic skill is that you can go ahead and write the electron configuration for the electrons in any atom on the periodic table. Let's take a look again at that whole energy type thing. Now, I just hand drew on the left here the layout of electrons within those orbitals, with the lowest energy here at the 1s and an increase in energy for these electrons as they move further from the nucleus. Almost looks like a step ladder. You probably have one of these in your textbook. All it is just showing that there's a jump in energy as you go, not just from one principal energy level to the next, but within the orbitals in the sublevels of those principal energy levels. Why am I showing you this? Well, right now, for the valence electrons, those 4 electrons, which for carbon means that I want to form 4 bonds to get to a total of 8 valence electrons, which is the most stable electron configuration for the majority of atoms on the periodic table, with the exception of the small atoms, which would be 2, and have the electron configuration of helium. It doesn't look like carbon's going to form 4 equal bonds. But yet, that's exactly what we see in methane. So let's take a look at methane. Here you see the structure for methane, CH4. It's a tetrahedron. That's why it has the shape. These are 4 bonds situated where the hydrogens are far away from one another as they can be. But these are equal bonds. It's not like the 2s electrons for carbon are lower in energy than the ones in the p sublevel, and therefore it's not going to look exactly the same. They're 4 identical bonds. That's where the orbital hybridization comes in. Instead of having 2 electrons in the 2s and 2 electrons in the 2p, what we say is that carbon, as the central atom, the orbitals undergoing a hybridization where you end up with 4 equal orbitals as far as energy levels, known as sp3 orbitals. Carbon has 4 valence electrons. Remember, this is in the second level. And these arrows obviously are representing electrons, and therefore there are 4 spaces now where each one of the valence electrons for hydrogen can form the bond. Again, we have the electron configuration now for carbon when it's bonding with another atom, in this case hydrogen. It's going to undergo an orbital hybridization, and you're going to get 4 identical orbitals in the case of methane for carbon that are sp3 orbitals. The shape even changes. Take a look at your textbook, go online. Again, check out the link in the description below. Here is methane, the Lewis structure, and what you see in black are the 4 sp3 hybrid orbitals for carbon, and then each one of the electrons for hydrogen is in the 1s sublevel, and there's an overlap, right? Orbital overlap when it comes to bonding. That's how we get our 4 equal bonds. A lot of students don't get this right away. Quick way to know what the orbital hybridization is for the central atom, if you're asked it, after you draw the Lewis structure, count the number of bonds and the lone pairs on the central atom, and that tells you how many hybrid orbitals you have for that atom. For instance, we have ammonia here. Ammonia is a pyramidal shape, 3 bonds and a lone pair. The nitrogen electrons also go through sp3 hybridization. All right, the lone pair here counts as well. This is a good time to go back and practice Lewis structures, drawing them, following the steps for Lewis structures. You could find it in your textbook if you don't know them off the top of your head. You do need to memorize them. It's another skill, just like electron configurations. I want you to understand also double bonds only count once when it comes to orbital hybridization. If there are a second bond or a third bond that is not a hybrid orbital. In those cases, it's a pp overlap. Let me show you an example. Think of carbon dioxide. If you can, draw the Lewis structure. All right, for carbon dioxide, here you have the layout of atoms. Carbon ends up forming 2 carbon-oxygen double bond. The orbital hybridization for carbon, that only counts for 2 of the 4, so therefore we have an sp and an sp, right, overlapping, and the other is a p overlapping with the p from oxygen. So if you're asked about the hybridization for CO2, it's sp. Why? Because of the double bonding. I know it sounds more complicated than it is, but it is not. You have to go back, though, and practice. First thing I would suggest, any ones that you went over in class, hide how you did them, do them again. Go to the textbook, do the ones that are in the chapter, hide the answer, and practice. What's going to happen over time is you're going to just see them. Now, these hybrid orbitals, if you take a look here on the right-hand side of the screen, This is a list of the common ones: the SP, the SP2, SP3, SP3D, and SP3D2. This is for what's known as the expanded octet. When you get to the third principal energy level, the atoms there, since you have the D sublevel, you can have valence electrons that are in the D sublevel. For example, SF6. If you're asked to draw this particular molecule, you end up with the octahedron shape. And as far as the hybridization for the 6 now, orbitals for sulfur, they're each going to be an sp3d2. So 6 of those overlapping with the P from the 6 Fs. It's worth your while to go back, practice along with those Lewis structures. Any questions you have, you can leave them in a comment for me, and I'll address them for you as best I can. As always, keep working hard and good luck.